Hi sir, so today I'll like to demonstrate on how to apply concepts of ODE to model equation related to Newton's law of cooling. So according to Newton's law of cooling, the rate of change of a temperature of a body is proportional to the temperature difference between the body and surrounding. Hence, we can actually write a relation into it where the rate of change of temperature is proportional to T minus T surrounding. And in this case, we can actually let it become T prime equals to K times T minus Ts. Any proportional relation, we can actually add a constant in front of it, so it will actually become a proper equation also. So we just play around with the equation and arrange the equation. So doesn't this formula seems familiar to you? It's actually a non-homogeneous linear ODE equation. Hence, we will actually need to find the integrating factor for it. So P, it will become negative K. So Ft would actually equals to E integrating e to the power of integrating negative K in terms of dt equals to e to the power of negative kt. Hence, we will actually like to multiply the integrating factor into the previous equation. So it will actually become e minus kt equals to negative k times e to the power of negative kt times ts. Hence, this will be our equation for it, and we will actually like to simplify it by d over dt equals to e to the power of negative kt times t equals to negative ke negative kt times ts. Hence, we would like to remove the d over dt sign, so we will actually like integrate both sides. And by integrating this part, we will actually get e to the power of negative ktt. It's the same, and for integrating this part, we will actually need to divide by negative k. So it will actually become e negative kt times ts plus c. Never forget the c. Hence, for the we need to simplify this equation by multiplying it by e to the power of kt. Hence, it will actually become t equals to ts plus c e to the power of kt. Hence, the general solution for Newton's law of cooling will actually become temperature in terms of time equals to the surrounding temperature plus Ce to the power of kT. So next, we will actually apply a real-life application onto this equation. So now for the real-life application where the air temperature is 5 degrees Celsius, so we know that the surrounding temperature is actually 5 degrees Celsius, Ts equals to 5, and water cools from 100 degrees Celsius to 75 degrees Celsius in 5 minutes. So initial temperature would actually become 100 degrees Celsius, and after 5 minutes, it will actually become 75 degrees Celsius. So with these three information, from the previous general solution where Ts plus CEKT, so we can actually replace the surrounding temperature with 5. So yeah, then we still have another two constant for it, so we need to use the two information here to find the constant. So when T0 equals to 100, so 100 equals to 5 plus CE K times 0. So e to the power of 0, we will actually get 1, so 100 equals to 5 plus C equals to 95. And for K, when T5 equals to 75, so 75 equals to 5 plus 95 E 5K. So if play around the equation,
170 over 95
equals to 5K. So we will get the value of K equals to negative 0.061. So in the end, we will get the final general solution where temperature in terms of T equals to 5 plus 95 e to the power of negative 0.061 T. Hence, by using the last general solution, the final general solution, we can actually find the last requirement where how long will it take for the water to cool to 10 degrees Celsius. So T equals to 10, where 10 equals to 5 plus 95 e to the power of negative 0.061 T. So play around with the equation, we will get ln 5 over 95 equals to negative 0.061 T. So we will get the time equals to 48.27 minutes. So I've plotted a graph for the equation obtained, which is the general solution. So it has a relationship represents a rapid decline of temperature that gradually slows over time. So when time reaches infinity, it will approach 5. So this also obeys the law of equilibrium where the equilibrium state is at 5, it won't go down towards it, it won't go down to 4. So it obeys the law of equilibrium. That's all for my demonstration. Thanks for listening.